Hello. And welcome to a recorded demo, made by IZT, OHB, and IMPO-RF. The demo includes short presentation of IZT, S1000 capabilities, GNSS simulation, and spoofing capabilities. For any inquiries, feel free to contact us.
So we are based in Erlangen in Germany. We have about 60 employees. There's mostly engineering, so we have a lot of engineering stuff. We do in the house also the building of the equipment, the integration and testing. And we offer product business, we offer development, we offer turnkey solutions. And our business is mainly in the RF monitoring, radio direction finding, satellite terrestrial channel emulation, signal sources for different test signals, and also some products for DAB, DRM broadcasting. Just a quick overview of our receivers. So we have different receivers of the R3000 series. They are mainly used in the, let's say, ITO monitoring field. They are used for recording RF signals for bandwidth up to 24 megahertz. So they're very good quality in the market, well established and used a lot. Okay, then we have the 5000 series. So there's the series for 120 megahertz instantaneous bandwidth with different mechanical enclosures. So some are for 19-inch racks, others for waterproof, passive cooling. So they are widely used in different areas. Very high quality, very good signal quality as well. So then we have a very compact receiver. So it's half size of 19-inch, so you can have two of them in one rack size. So they are DC supplied, can be used for monitoring in the car, etc. Important is also the built-in GNSS time reference. So then this is a different variant of this. So it's very good shelter, so it's proof, it's safe, it's convection cooled, harsh conditions can be used. So, but principally same inside interior than before the 5060. So that's some record playback equipment we have for use in the car. So this very widely used receiver 3301. So it can be recording synchronously multiple signals at the same time. And the replay can be with one of our signal sources, which is also used today for generating the GNSS signals. So we have software for different applications, so we can do some more. Hello again. So we have receivers controlling, we can do capturing of individual spectrum areas. We can do segmentation, automatic classification, and decoding. This is, if this is interesting, we can do a separate session. And yes, so that's a software for everything which is in comparison, which is used for the receivers. Okay, then other business field is the satellite emulators. So we use them for doing the full testing the full link from the satellite to the earth stations and back. So bidirectional. It can have multiple links at the same time, depending on the let's say the way how you configure the system. So that's the 6000er or the 5040 series, and we have a single unit with one RF in, one RF out for the C3040. Okay, then we come to our signal sources. So there we have an S1000, which is a 2H unit, and we have the S1010, which has also an integrated server. So this is used for civilian or military applications, so it can generate multiple signals at the same time, up to 32 signals individual content. The signals can be any kind of sample rate up to a maximum, of course, and all the channels or signals can be streamed in real time. So we support a wide standard of, let's say, radio testing signals, and also the GNSS for GPS, Galileo, and etc. There we keep for the civilian modes. A frequency range from 9 kilohertz to 18 is possible, so there's a variant up to 3, up to 6, and up to 18. And it's widely used in the business and some other areas. So then we come to the GNSS simulator. Today we will see our signal generator S1000 GNSS, which is also located in near sense. It can do live signals, it can simulate interference, it can also replay recordings, and all the satellite standards with a total sum of up to 208 GNSS signals can be simulated at the same time, and also generated on the RF outputs at the same time. So this is just a block diagram. So we have real-time modulators inside the FPGA implementation, and we have a connection to the simulator from Sasha. It's GNSS Explorer simulator. This a real-time GNSS simulation software, and this is connected to our signals hardware with a 10G interface. And the simulator is running on a PC-based software solution. So this is just a few screenshots of the solutions Sasha has provided. So there's a routing software which can also simulate speed camps, tunnel, charging stations, and all equal trigger points. You can route via Google or TomTom, I think it was the tool we have, and this can be used for doing a long time driving with real let's say charging stations, speed camps, and tunnels. You can put them into the location while you generate the signals. So then we have a screenshot of the GNSS software. This is just in here. And then we have the screenshot of our signal source we will see today for generating the GNSS signals. So then for the next field we have monitoring and radio DF systems. So just a short overview of what we have. So we have one which is integrated in a South African Atlaris antenna. Then we have one for Eurocontrol air traffic analysis and checking where the signals of the communication is coming from. So this is also in a couple of installations in Europe. So this is one of our systems on our roof. So this is a non-switching receiver, so high performance. And we also have a solution for a DF system, not only with the integrator, so we also have our own direction finder software now. Yes, so this is what I told already for the ATC and VTS applications, so for air traffic control. This is also with robust outdoor enclosure with a lighting protection and very robust also for high speed and tornado or something like that. So we also have a system which is used for on the outdoor with a larger antenna arrays. So this was one of our field tests where we did that. Yeah, this is one of our systems. We do full installation for the, let's say, one of the Maastricht centers. So this was also built from our company completely up to for everything. Okay, so the receiver itself is based in this outdoor enclosure here, including the PC software, and after that you go with a 10G to the control station. All right, let's just follow. So you see the size what it is. Okay. We also have a TDO location finding. This is used with different receivers in different positions and with a high reference clock or with a high, we can do a location finding for signals, but you need at least, of course, 3 individual receivers. Okay, we also have some software for de-hopping. Maybe of some interest. So that was my presentation, very short. And now I think we can go after some questions. If there are questions, I'm happy to answer them. And then we will go to the live presentation for the GNSS system.
About the simulator, can I use it in a lab without any antenna and to put in like a fixed place that the coordinates that I want him to receive, and it will simulate like I receive it from a GPS receiver, including the 1 PPS?
Yes, of course you can do that.
Thank you.
Basically, this is already handing over to my part of today's meeting. So this is how I will use the setup that we have in our lab to show the capabilities of the GNSS simulator. You should be able to see my screen now. So I don't have any images of the hardware here. Basically, the setup that we use is the one that Horst already had on his presentation. With the IZT S1000 as a signal generator platform, and this S1000 together with the PC that is used to control it forms the complete GNSS simulation hardware that is required. So this is in my case, as you just described, standalone in our laboratory. We can, of course, connected to external signals coming from an antenna with a coupler. We could mix and match the real signals and the simulated ones. Right now, I have just one U-Blocks receiver that I connected with a direct cable connection to the simulator. So here, this is the screen of the U-Blocks receiver. It does not yet receive any signals because it is connected to the simulator, and that's still turned off. And this screen, as you see here, is from my laptop that I use for the meeting, because on the signal generator, I don't have the connectivity in the Teams app. I have a screen or remote desktop connection to the signal generator that I connect to. So maybe I can do this a bit bigger. Then you should be able to see it. So this, what you can see now, is the main user interface of our GNSS simulation software, which is called Explorer, and as I said, runs on the S1000 signal generator platform. I prepared a demonstration scenario for spoofing, so I will just open this to show basically the capabilities of the system. I will now go through the individual settings briefly. of the simulator, and then I will start the simulation so we can basically then see how this how the u-blox receiver reacts to this. We are now at the general settings page. Here in the general settings, we can do some basic configurations here, and we can choose which signals we would like to simulate, we would like to generate. This spoofing signal for or spoofing demonstration for better visibility in the u-blox now, I restricted to the GPS L1 signal only, but as you can see here from this list, we support basically all the civil GNSS signals that are in the air nowadays. The next page is a very simple one, actually. It just configures the time. So as you know, that GNSS signals or systems do not only provide a positioning information to the receiver, but also timing. So the time is something that can be configured. In this case, it is just any random time that we picked when we first created that specific scenario. Basically, we see that the scenario has a duration of 12 minutes. As Horst pointed out already in his presentation for this automotive route planning add-on, the simulations can get arbitrarily long. So we did simulations for more than 48 hours continuously without any issues. There is no theoretical limitation on the duration, and the time can be defined here or in the specific variation that is used just for generating spoofing signals, not this flexible simulation engine here. We could also select to just use real time, then the spoofing signals will be generated in sync to the live GNSS signals. For this, we would need to connect the reference GNSS receiver that gives us the time reference that we can connect to, and then from this reference receiver, we will take the time and the satellite constellation information and generate the spoofing signals accordingly. So in this demonstration, I just keep the time that is simulated. We can then later observe that same time in the u-blox receiver. The next configuration that may or may not be of interest for a simulation is the satellite settings. So here we can control all the simulated satellite constellations. Right now you see I just selected GPS in the general settings, so I'm just simulating that. And here we have a list of all the individual 32 GPS satellites that we simulate. And for each of these satellites on the map, we see basically where the ground track plot is during the selected time of simulation. This is something that this is relevant data for spoofing scenarios, because in spoofing cases you need to synchronize also this data to real world data. For this, we have several ways of importing the actual live data, or we can also directly grab it from a reference receiver in the spoofing software. For laboratory setups, for specific tests, there is also possibility to actually edit and modify all the individual values. So you could, for example, simulate something that happened for 2 Galileo satellites. They have been launched in a wrong orbit due to a launcher failure in the end, and then they had a higher eccentricity than nominal. So this is something that you could use the simulator for, to test what happens in the receiver if a certain value goes out of its valid range. This is just one example what you can do with the simulator. You can also, if you just want to have a relatively simple simulation setup, you can also just choose to use default satellite orbits. Then there will be no no specific orbit perturbations. There will be no short-term errors that are modeled. We will just use the default satellite constellations as they are defined in the ICD. The same is basically true for the atmosphere. As you might know, the GNSS signals are significantly affected by the atmosphere when they pass through the atmosphere. Specifically, the ionosphere and troposphere are relevant here. So we, of course, model in the simulator both of these effects. Basically, these two atmospheric layers delay the GNSS signals as they are then approaching the receiver. In both cases, you can just select to work with a default model that will just work out of the box, and there is no way to misconfigure it. Or if you want to model a specific situation, you can choose to use Klobuchar or NICWIC models, which are the common global ionospheric models, or you can go with a Ionics tech maps, which is a gridded, high accurate model for ionospheric data. Yeah, so these are the atmosphere settings. I'm reverting to default now. And then, yeah, maybe the most relevant setting in a GNSS simulator, as it is the actual receiver position or trajectory. As you can see here from the map, in this simulation, we prepared a trajectory, basically starting from the IZT offices going to the inner city, following roads. Of course, here you can see the trajectory is defined based on waypoints. So they can be arbitrary. They can be used to model aircrafts, drones, cars, stationary receivers, pedestrians, even satellites, or something similar. So basically, there is no limitation in the dynamics that can be simulated for the receiver. This is only a legal limitation. So if we need to go beyond a certain level of velocity or altitude, the software becomes export restricted. So in this case, we would need to go this process of getting an export license before. But if we stay below that limit of dynamics, there is no legal issue as well. Beside the trajectory, which can be chosen based on waypoints, or also in an alternative way, including velocity and acceleration based on a state vector model. Beside that, we can also model the actual position of the antennas. So this is, yeah, I don't want to go into too much details here. What you can basically do is you can model the gain pattern of the antenna, and you can model also where the antenna is actually placed on the receiver. And then this means if the receiver rotates in a certain direction, for example, the antenna moves along this rotation and follows that path according to its position and its own antenna attitude. This is, yeah, useful for creating more realistic tests of moving objects. For example, if you would simulate, I don't know, a rocket or something like that with the antenna on a certain position and that rotates, then you will see this has a significant effect on the GNSS satellites as they are received, and this can be modeled and simulated here accordingly. Multipath is something that we can also simulate. This works based on a statistical model where you can choose so-called obstruction masks, which define the multipath environment depending on the time. And yeah, then the additional multipath signals, the reflections that are received are modeled according to the statistical model based on the environment that you can choose here. This is useful, for example, in automotive use cases to get them a bit more realistic, or in any more urban scenarios, but of course can be deactivated as well. Now, maybe more relevant for the purpose of this meeting today is the interference section of settings. In terms of interference, we can simulate jamming or spoofing signals, or both in combination. And we also have something that is called spectrum match jamming, which is a bit more sophisticated type of jamming where the jamming signals actually mimic actual GNSS signals, real GNSS signals, but without any navigation information. So it is not spoofing per se, but it is something in between jamming and spoofing. It is something comparable. In terms of jamming, we can add basically multiple jammers if we like, and each jammer is defined by its own position, where it is located and emitting the signals. Right now, yeah, it is at a completely different location because I didn't configure it. And then each jammer has a certain transmit power that can be configured, that can also vary over time, same as the position. So the jammer can be stationary, but it can also be moving. And we can select different types of jamming signals. So the most common, like personal privacy device style jammers are SCW or chirp signals. So we could choose a chirp with a certain bandwidth and a sweep duration. We could make them pulsed or continuous, and then basically the jamming signals are generated in addition to the GNSS signals. So for this scenario that I've prepared, I did not include a jammer, but I add a spoofer. In this case, our spoofer is defined as can be seen on the screen here. Basically, for the spoofer, we can also define a certain start and stop time. We can define which signals are to be spoofed. So we can create scenarios where the receiver has, for example, tracking GPS and Galileo satellites, but only the GPS signals are spoofed. We can also spoof just selected individual satellites if required for more sophisticated scenarios. In this case, I chose to just spoof all in-view satellites. And then the most relevant part for the definition of a spoofing scenario are basically these three positions or trajectories. So there's one thing, the spoofer has its own location, which is not necessarily the same as the receiver is. So here we say the spoofer is stationary here at this position. Then the spoofer needs to know where the target is that it wants to spoof. So this is actually the position of the receiver that should be spoofed. In the case of our simulator, we can configure them as I configured them here in this scenario to match perfectly the actual real receiver motion. But in a real spoofing use case, this will not be the case. You will never have perfect, without any uncertainty, knowledge of where the victim receiver is. So in this case, modeling this target position slightly offset to the real receiver position is useful for assessing how successful a spoofing attack can be. And then finally, the simulated receiver position is what the spoofer actually wants to achieve. So this is the position or the trajectory that should be injected into the receiver. So in this case, we see here if we look at it on the map, that this green line is the actual receiver position, and the spoofing will start basically here at this intersection. And instead of following the highway on the map here, we'll turn away from the highway and move to the north here, and then come back south in the end. So we should see later in the U-Blocks receiver that the U-Blocks will follow that spoof trajectory and not the actual receiver trajectory. Now, as it is configured now, this scenario is configured. There is more settings that I didn't explain. There is also more deeper configurations that are in text-based configuration files available for a lot of sophisticated stuff, but this was basically a very basic spoofing simulation. So I'm just starting the simulation now by clicking the simulate button here on top. If I do this, you see this splash screen loading. That basically now is configuring the hardware according to what we defined. So it configures the center frequency for the RF output. It configures which signals are available, which modulators need to be enabled, and then the simulation starts. So this is how the main view looks like during the simulation. We have a central element here, which is the map, which shows us position of the satellites and the receiver. On the right-hand side, we see an overview of the individual satellite signals. Also, we have a sky plot, or we can see carrier to noise ratio of the individual signals as they are received, or as they are simulated, sorry. And here in the bottom, we see some details on the spoofer. It's not yet active. It will turn on after 3 minutes, I think what was configured. And we see some live data on the receiver. Now I can click here this button to follow the receiver in the map. So this is, as you can see, how the trajectory looks like. The trajectory updates in this configuration with an update rate of just 1 Hertz. So you see basically the second by second steps. And then let's exit this view and see what the receiver does. Maybe I can start this again. I don't know if I could somehow clear the map, because of course I tried it first, and now you see the old trajectory is still overlapping. I will just open it again to see it in a bit better visibility. So let's connect to the device here. So you can see basically that the u-blox receiver is connected with its USB connection. I'm adding it here, and then I start to see some data. Let's prepare the view a bit. Okay, so now you can see what we want to see, that the u-blox receiver is following here this path, which, if we go back to the simulator, actually matches the simulated path. Now, because I reopened the U-Center software, we lost the beginning, but we see that in real time it is following the same trajectory and the same road. What we also see on the bottom here is that we track all the same GPS satellites, basically with their reported carrier to noise ratios as they are simulated by the simulator. We see here also sky plot, and that the receiver follows the trajectory. Now if we go back to the simulator view, I'll turn off this follow here. We see that now the spoofer is already active. So now we see at this point in time that the green and the orange dots, which are the actual receiver position simulated, and the spoofed position, start to deviate from each other. And we see that the spoofer will take this turn and leave the highway. And we can observe, hopefully, we can observe that same thing in the receiver. So this shows that now our u-blox receiver actually receives two GNSS signals. One is the authentic signal, which actually continues its path here on the highway. And the other is a set of signals for the spoofer. So each satellite is simulated actually twice, once for the spoofer and once for the authentic signals. And our u-blox receiver follows that spoof trajectory without any indication that something is going wrong, without any indication that there is a spoofing attack ongoing, just follows the same trajectory. Of course, we generate our spoofing signals with some noise to maintain a realistic carrier to noise ratio level. So this is something that looks perfectly normal. It is not suspicious at all for the receiver, but still the receiver follows our spoofed path. And Now, in this demonstration, of course, we have both trajectories actually simulated. We have a simulated set of authentic signals and a simulated spoofing set. But if you do the same thing in a synchronized way to the real world GNSS signals and just simulate the spoofing signals in synchronized way, the result in the receiver will be basically the same. In practical realizations, what is very important to maintain is this synchronization to the real world. So if you really want to spoof in a real world scenario, you need a reference receiver to synchronize to that and to get some orbit data, some satellite constellation informations. And you need to maintain a realistic power level when actually transmitting the signals via an antenna, a broadcast antenna. These are the two things that are taken care of in our spoofing product, which is a specific variation of our simulator. So this software that I showed today and this laboratory setup is the lab setup to simulate everything in terms of GNSS. And there is a specific variation of this with a bit more simplified user interface to just focus on the spoofing, on actually transmitting spoofing signals in reality. I don't have this as a demonstratable lab setup here, but it is based on the exact same hardware and the exact same software in the background. So I think this is a valid demonstration of both use cases. Okay, this basically brings me to the end of my presentation. Are there questions to that?
Yeah, I have a question, if I may.
Sure.
You transmit this information, the spoofing information, on one RF channel, I guess.
Yes.
Can you do it on both RF channels and with the applicable phase difference, at least, and maybe amplitude difference between the two elements?
Yes, this can be done as well. So the S1000 has two RF outputs. We can use both RF outputs for different sets of signals to have a bit more diversity. This can be useful in a realistic setup. Yeah. So what we can do here is output the authentic signals from one output and output the spoofing signals from the other output.
No, that's not what I mean. I want to get both authentic and the spoofing signal as both RF channels. With the difference, simulating basically a situation that you have two antennas getting the whole information.
Sure. This is something that can be done here. Basically, in the receiver, you can configure multiple antennas. So we could add a second antenna here. The second antenna may have a slightly different position here. So we can say it is, I don't know, 0.5 meters in the V1, so in front of the vehicle.
Yeah, doesn't really matter.
Yeah, and it doesn't really matter. Yeah, and then in the end, we can configure in the S1000 GUI that these antenna 1 signals go to one output and the antenna 2 goes to the other output. And then the question is what to do with this information. You can connect it to a receiver that is capable of connecting to two antennas, or you can also again just mix them to see what happens.
Yeah, that's my problem. I'm connecting it to another system, which eventually will connect to the receiver. Yeah. But I want to make sure that I can really simulate real life situation where I have a spoofer and I have real life satellites, and all transmit and being received by the two antennas.
Yeah. Yes. Sure. What's also a possibility here for the spoofing here in this case, you see that my target position is perfectly matching the receiver. This is the best case for a spoofer. By modifying that a bit, you can inject certain synchronization errors in terms of the spoofing signals on signal level. So in this setup on signal level, no matter how many antennas you will simulate, each spoofing signal's correlation peak in the receiver will exactly match the authentic peak. So this is easy for the spoofer. Of course, if you change this a bit, the spoofing signals needs to be higher to take over the correlation peak. And this can be controlled here by this target position and by the spoofing power.
All right.
And you can also add an additional offset to all the spoofing signals. This is here defined in meters, basically on signal level, how much off you want each spoofing signal to be.
Okay, thank you very much. I guess the same apply. You were talking about spoofing, but I guess the same apply to jamming, right?
Yes, of course. So for jamming, the same is true for jamming. What we what we cannot do for jamming is add a kind of synchronization offset to spoofing, because there is no such thing as synchronization. But you can add the simulated jammer at its own position, or the simulated jammer position can exactly match the receiver position. If the jamming position exactly matches the receiver position, the power that you define here will be directly used as received jamming power. So you can create a scenario with a constant received jamming power. But if the positions do not match, we will actually consider the path loss and compute the attenuation from the path loss here. So then the jamming signals will change in power over time. Okay,
and you talked about really simulating a situation where the jamming, the jammer is transmitting similar or legal messages, but with no information in it.
Yes, this is
called simulate it.
Yeah, this is called spectrum matched jamming.
Spectrum matched jamming, okay.
Where basically we have a certain type of GNSS signal that is generated at the jammer and transmitted. This is basically just generating the PRN sequences for all the, in this case, GPS signals, satellites that are in view at the time. For each of these, we will generate their PRN sequences, but without any navigation data. What this does to the receiver is actually quite interesting. So we tested it with same type of U-blocks, but also other receivers. And in the U-blocks receiver, you will see these signals are being tracked. They will have a good carrier to noise ratio, but you will never get a position because there is no time reference in the signal. So this is something that is not obvious as a jamming, but it acts as jamming in terms of it is denying the service, but it's not jamming the receiver by overpowering it with noisy signals.
Okay, thank you.
You're welcome. Further questions?
Does the system have to be connected to the network, to the internet, for downloading different information and stuff, or?
If you want to download, there's one example here. You can download the the live satellite constellation data for all the constellations from the internet. If you want to do this type of thing, then yes, there needs to be a network connection. Otherwise, the system does not require any external connections.
Okay, thank you.
Maybe for updating the map data for a while.
Yes, there is. If you look at the maps, where's the map? Here. If you look at the maps, these are in this view based on OpenStreetMap. So this is a live updating, but there is also, in the simulation view, there is also an offline map, which is just the basic preloaded map of country boundaries, and I think some rivers are shown. So not really accurate, but if you want accurate map information, yes, this is also a thing where you need some internet connectivity. Okay. Choose an offline map like this style as well. Yeah, these are basically the only two areas where we would need some network connectivity.